This is Mr. Parvaiz with Henrico High School. This particular lesson is a little tricky because we're going to talk about circular motion, but we're no longer going to talk about a horizontal circle. We're not going to be talking about an object that's traveling in circular motion when you're looking at it from above in a horizontal circle on a horizontal plane. We're going to talk about an object that's traveling in a vertical circle. So this actually right here is a side view. You're looking at it from the side. And I'm going to go ahead and simplify all of this. By showing you how each one of those vectors come into play. So remember in the beginning of the class we worked with a cup of water and we attached it to a string and then we rotated the cup of water in a vertical circle, and the cup of water stayed in that circle until the string broke. When the string broke, the cup of water shot off in a direction tangent to wherever it was on that circular path. So this is that particular example. It's talking about the cup of water that's attached to a string and it's rotating in a vertical circle. It also will apply to something like if you've ever been to a circus and you've seen that motorcyclist that rides inside, he rides a motorcycle, he or she rides a motorcycle inside a sphere. It's a metallic sphere. So they make a vertical circle in that motorcycle. So it's the same idea. It also applies to many roller coaster theme parks where you go into this park and you get into this ride and you're standing on a circle, and then all of a sudden the circle starts rotating, and that become a horizontal circle can switch to a vertical circle, and you then they remove the floor and you stay, you don't move. So we'll talk about more about that in class. But anyways, so you have to make sure you're looking at this from the standpoint that you're looking at it from a side view. This is a vertical circle, and we have a cup of water right here, and the cup of water moves as you rotate it in that vertical circle, and the cup of water is attached to a string. So I'm going to draw the string in orange, and the drawings may not be perfect, but we'll do the best we can. So the string shows that it's attached to the cup. So the string is the thing in this case that's preventing the cup from leaving the circle. So that means the string is what's generating the centripetal force. So then you would say that the tension force in the string is equal to the centripetal force. So keep that in mind. The tension force is going to be your centripetal force. Let's go ahead and draw the direction. So the cup is rotating in this vertical circle. It's going counterclockwise. Let's also go ahead and draw the velocity vectors. So the velocity vector is being drawn in purple. If you're drawing this on your piece of paper as notes, make sure to label it V because that's your velocity vector. And the velocity vector is always tangent to the curve. You've done this before with me, but I'm still going to go ahead and put it on here. So the purple vectors are your velocity vectors. And then this is the tension force. This is the force that the string is exerting on the cup. So this is your centripetal force. So right now there's a tension force in black. So label that capital T, that's your tension force. And the tension force continues to pull towards the center. But you notice that over here, it's pulling downwards. Over here, it's pulling to the left. So that will come into play in a little while. So the tension force, label all your black vectors as your tension force. There's also one more force we have to keep in mind. When you're traveling in a vertical circle, you also have to take into account the force of gravity. So I'm going to draw the force of gravity in this turquoise color vector. At this point, the force of gravity is pointing down, and the force of gravity will always point down. The thing we have to take into account is when does the force of gravity point in the same direction as the tension force, the black vector, and when does it point opposite to the tension force? And you'll notice that occurs at the top, where you notice that the force of gravity and the tension force, the turquoise and the blue vector, are both pointing down. And you'll notice at the bottom, the force of gravity is pointing in the opposite direction. The force of gravity, excuse me for drawing, the vector isn't straight, but anyways, the force of gravity is pointing down, the tension force is pointing up, because the string is pulling up while the force of gravity is pulling down. So these are two important parts. At the bottom, where the tension force is in the opposite direction to the force of gravity, and at the top, where the tension force is in the same direction as the force of gravity. So I'm going to go ahead and analyze these two locations, the top and the bottom, on the next screen. First I'll do the top location and then we'll do the bottom location. We're going to choose downwards to be the negative direction and upwards to be the positive direction. So first, we're going to analyze the top portion, and we're just going to take into account the two forces that are in play over here. The two forces that are in play are the force of gravity and the tension force in the string. So at the top, the equation is going to look like this. You're going to say, well, the two forces that are responsible for my centripetal force, the two forces that are acting on my object, you're going to say at the top, the centripetal force is due to my two forces, and both of these forces are pointing down towards the center. So they're pointing downward, so we're going to label both of them negative. So you can say, okay, one of them is my tension force, and the other one is my force of gravity, and the force of gravity is right here. So this just simplifies to minus the force of gravity, and this is a powerful equation because many times they're going to ask you to solve for the tension force. And if they ask you to solve for the tension force, all they're saying is take this equation and rearrange it for T. And that's easy to do. I'm going to go ahead and plug in mv squared over r for the centripetal force. And this is your equation for the object at the top of the circle. And then you just have to solve for the variable that's given to you. So if they say find the tension force, then they're saying solve for t. So then take your t to the left side and bring your mv squared to the right side. And then plug in your values and you'll get your tension force. If they say to you, what's the minimum speed that the cup has to travel so that it can make it to the top of the circle? The minimum speed. So that means the rope is barely pulling on the cup. It's the force of gravity that's doing all the work. So if they ever gave you a problem and said, what's the minimum speed the cup has to travel at and still make it to the top of the circle, then all I want you to do is I want you to start with this equation right here. But because the minimum speed, that means the rope is very laxed. There is no tension in the rope. So then make t 0. And if you make t 0, your equation will simply be mv squared over r equals negative mg. The m's are going to cancel out and solve for v. That'll give you the minimum speed the ball must have so it can reach the top and then come back down. And just keep in mind, whenever they talk about the minimum speed, they're saying this force is becoming 0. They're saying the only force that is impacting the object is the force of gravity, because we can never take that force away. So then in that equation, this component, the t component, is going to become 0, and your equation will become mv squared over r equals negative mg, and you can solve from there. Let's go ahead and analyze the bottom. So now we're going to analyze the bottom part. You see in the top part, both the tension force and the force of gravity are pointing the same direction. Now, the tension force is pointing up, and the force of gravity is pointing down. So we're going to go ahead and analyze the bottom part on the next slide. So for the bottom part, the centripetal force is due to the tension force. Now the tension force is pointing up, so it's positive. And the force of gravity is pointing down, so it's negative. These two forces make up the centripetal force. And you can simplify this equation to T minus the force of gravity. Centripetal force is mv squared over r. T is the tension force, and the force of gravity is mg. Once again, if they say solve for the tension force at the bottom of this vertical circle, they're saying solve for t. All you're going to do is take your negative mg to the other side, and your equation will be mv squared over r plus mg equals t, and that'll give you the tension force. Then they may also ask you to solve for the radius or the v. Just plug in your variables and solve from there. So this is the bottom of the circle, and this here is the top of the circle equation right here. These equations will stay the same. The scenarios will differ. Let's say it's not the string. Let's say you have a vertical circle, but you don't have a string that's keeping you on that circular path. Let's say this is the motorcycle. Let's say the red dot is a motorcycle traveling inside of a metal sphere, and it makes this vertical circle every time. Well, in that case, the motorcycle is not attached to a string, so there is no orange. You don't need to draw the orange part. However, everything else stays the same. The motorcycle's velocity is going to be in purple. So the velocity vector is correct if it's a motorcycle going around in a vertical circle. you're going to say, what's generating this force? What's generating the black force? Well, in that case, it's the metal sphere that is preventing the motorcycle from leaving the sphere. So it's the metal sphere that's pushing inwards. And that is called a normal force. So if it's an object that's riding, like a motorcycle is going around in a vertical circle in a metal sphere, and then it'll be the normal force. You won't call this the tension force, you'll call this the normal force, because it's the force that the surface is exerting inwards. This is still the force of gravity. The turquoise one will be the force of gravity, the black vector will be the force of will be the normal force. So over here you'll say the normal force and the force of gravity are pointing down. You'll say over here that the normal force is pointing to the right. There should be a correction over here. This turquoise vector shouldn't be pointing towards the right. This turquoise vector is the force of gravity. I should have drawn it pointing down. Excuse me for that error. The black vector is pointing in the right direction, but the turquoise vector, which represents the force of gravity, should be pointing downwards. And over here at the bottom, when the motorcycle reaches the bottom of the circle, the force of gravity still points down and the normal force still points up. So once again, let's analyze the scenario. We'll analyze the top portion and we'll analyze the bottom portion. Let's start off by analyzing the top portion. In the top portion, you're going to say, okay, my centripetal force is due to my two forces, my normal force and the force of gravity. Both of them are pointing down. So normal force plus my force of gravity. And you're going to say negative Fn minus Fg. And right here, you can plug in your values. You can say mv squared over r equals negative Fn times minus mg. So if they say solve for Fn, then simply just take Fn and put it by itself. The simplest way would be to take Fn to the left side and take mv squared to the right side. You can do it that way. There are a lot of different ways, but just saying, if they say find the normal force, that's how you find the normal force. Now, what if they said, what is the minimum speed the motorcycle can have and still make it to the top of the circle? So what is the minimum speed the rider must give the motorcycle so he can get to the top and then come down? What's the minimum speed? Well, when you talk about minimum speed, you're talking about the motorcycle getting to the top, but it's barely touching the track. It's barely touching the track. And it comes back down because the force of gravity is then the only force impacting the object. Because if we're talking about the minimum speed, then that means that the motorcycle is barely touching the track, so the normal force will become zero. This turquoise vector will become zero. So it's just like the cup, the cup of water problem. We made the tension force zero. When you talk about the minimum speed, the tension force becomes zero. And if you're talking about a motorcycle, then the normal force becomes zero. So if I ever asked you a question, give me the minimum speed the motorcycle must have to make it to the top of the circle, all I'm saying is make your normal force zero, because the motorcycle is barely touching the track at that point. Then your equation will be mv squared over r equals negative mg. Your m's are going to cancel out and you simply solve for v. And that'll give you the minimum speed the motorcycle must have at the top of the circle and still be able to complete the circle and come back down, because in that case the only force that's acting as a centripetal force is your force of gravity. Let's quickly go ahead and analyze the bottom of the circle. Just remember at the bottom of the circle, the normal force is pointing upwards, the force of gravity is pointing down. So I will go ahead and do it just like we did the cup of water scenario. We'll say the centripetal force is due to the two forces, the normal force, which is pointing up, and the force of gravity, which is pointing down. And then you go ahead and plug in your values, mv squared over r. Oops. This should be a little, oops, I'm just making this messier. Let's correct it, mv squared over r. And then you can solve for whichever variables you're looking for in that particular problem. But this is the equation for when you're at the bottom of the vertical circle. Hopefully this wasn't too confusing. Vertical circles are a little bit tough to grasp, so please take a look at the diagrams in your textbook. Go to YouTube. There are wonderful teachers who've done these lessons on YouTube that can also give you a different perspective.